So, magnetism. Okay, all right. So, just to start out with, just one quick fact, and that's this. If I have a North Pole and a South Pole, and it's on a bar magnet, and I were to cut the magnet in half, I might naively expect to get an isolated North Pole and isolated South Pole in my hands, but actually that doesn't happen. You actually get just pairs of North and South Poles, and that's because there's no such thing as a magnetic monopole in nature. And well, not necessarily there's no such thing. They haven't been discovered yet. And if you do discover one in your backyard, that's worth a Nobel Prize. So be sure to keep an eye out, I suppose. Okay, so let's talk about. We're going to first of all talk about wires and how they produce magnetic fields, and then after that we'll talk about how charge and wires respond to magnetic fields. So just first of all, the wires and creating magnetic fields. So the picture we usually start with is this one. We have a wire that's carrying, in this case, 3 amps of current, and we're interested in what the magnetic field is 2 millimeters away from that wire. So, sort of back up, when charge moves, it creates a magnetic field, and so around a wire, there's sort of this kind of circular looping structure for the magnetic field as it appears around that wire, and I've tried to draw a loop that's arcing out of the page in a solid as a solid line, and those that are diving into the page as dashed lines here. But this is sort of the structure that we see for the magnetic field. What we're asking for first is the strength of the magnetic field. And so to answer that question, we just use a formula. We say that B is equal to mu naught times 2 pi r, where B is the magnetic field, and mu naught is a constant. Mu naught is equal to 1.26 times 10 raised to the negative 6 in SI units. So for this particular example, we would write down the constant mu naught. I'm going to suppress units, even though that's a really bad form. I'm just trying to save myself some space. And we multiply or divide it by 2 pi r, where r is the radius between the wire and the point that we're interested in. We put that point in SI units because that's important. We get 3 times 10 raised to the negative 4 Tesla is what we get if we throw that into a calculator. And again, Tesla is the unit for magnetic field. So, whoop-de-doo, right? So, what about the direction? Direction's given by the thumbs up rule. And in general, I'm going to draw mittens here today because I'm feeling uninspired. Okay, if our thumb extends in the direction of the current, our fingers naturally curl in the way the magnetic field would curl around that wire. So in the case of the 3 amp wire here, I'm going to try to do it from your perspective. So 3 amps is headed in this direction. If I stick my thumb in the direction of the current, my fingers curl around that wire in the direction the magnetic field would curl, so it's curling this way. That point, that 2 millimeter point, that point that's away from the wire by 2 millimeters is below the wire, so you can see the magnetic field is going to be diving into the board at that point. And so we indicate that with the arrows or the feathers of the arrow as it disappears into the board. So into the board is the answer to that question. So those are wires. And let's go ahead and talk about loops here, and then maybe we'll do something a little bit more abstract. So with loops of current, okay, and maybe I want to know what the magnetic field is at a point in the very center. Let's say it's 2 amps of current and this distance is 40 centimeters. We use another formula that looks a lot like the one we just used, and that's mu naught I divided by 2r is the formula for the magnetic field in the very center of a loop of current. And so I'm just going to throw the numbers in for this problem just to get an answer so that we can talk about it. 1.26 times 10 raised to the negative 6, again, it's a constant. The amount of current running through that loop is 2 amps, and we are that loop is has a 40 centimeter radius. So we crank that out, we get 3.15 times 10 raised to the negative 6 Tesla, or if we want to be fancy pants, 3.96 or 3.15 microtesla is one way of expressing that. So that's the strength of the magnetic field in the center of the loop. If we want to know the direction, we have to use the thumbs up rule again. So if I stick my thumb, I'm going to do this in a different color here. If I stick my thumb in the direction of that current there, and I curl my hand, my fingers here, it's supposed to be a mitten. You can see my knuckles come out of the board here, and my fingertips dive into the board on the inside of that loop. I don't know if that's convincing or no. I'll draw it again on the other side. Maybe I'll get it right this time. Not really. Let's try that again. Okay, whatever. And so, yeah, here's our mitten. So you can see that our knuckles are coming out of the board and that our fingertips are disappearing into the board in the inside. So if we're inside the loop, in this particular case, magnetic field is directed into the board. There's another way you can do this too. You can use the same right-hand rule again, except we're going to say that our fingers now curl in the direction of the current I, and then your extended thumb now points in the direction of the magnetic field in the center of the loop. And so if I curl my thumb, say that loop's going in a viscerally direction here, so if I curl my fingers in that direction, you can see my thumb is pointed into the screen, which is in agreement with this other analysis we did. So, okay, so it's important just to say that magnetic fields are vectors, which means that when we add them together in a way that takes into account the fact they have direction. So just like with the electric field, say if I have a 5 Tesla field pointed this way and a 2 Tesla field pointed this way, and we want to know the net field as a result of these interactions, I wouldn't just add 5 to 2. I would, in this case, they point in different directions, so I would subtract the 2 and direct the field in the direction of the bigger field, and so we have a 3 Tesla net field pointed to the right in this particular way. And that's just because B is a vector, and it possesses directional information, so we have to be cognizant of that. So that's all the physics that's related to wires generating magnetic fields that we cover. You can stack a bunch of these wires together, you can make a solenoid and things like that, but for this particular review, I just want to touch on the bare minimum basics here, and those are that's it, right? Okay, so when charge is inside of a magnetic field and it's moving, and that's crucial, it has to be moving, and it's moving perpendicular to the direction of the field, it will feel a force. And that's what we're going to talk about next. So if we have charges in a B field, what type of forces do they feel? So let's say I have a charge, it's moving in this direction, and I have, I don't know, making it up, here's a field that's directed out of the board, pointed towards us. The question is in what direction will it feel a force, or will it feel a force at all? So the formula for a magnetic field is for the force felt by a charge moving in a magnetic field is QVB times the sine of theta. And I put that in a different color because usually for a lot of physics problems you sort of ignore it, but you take away from that one little term at least a few concepts. The first is this. Theta here is the angle between the velocity and the B field. So if theta is 0, that's another way of saying that the velocity is perpendicular to the B field, or sorry, parallel to the B field, then what happens is the particle doesn't feel any force at all. So if you're moving parallel to the magnetic field, and then there's no force felt, okay? Usually we assume that, as is the case in this example right here, that the velocity is oriented perpendicular to the magnetic field. So in this case, here's the direction of the charged particle. You can see that. You can see the magnetic fields pointing out of the board. That right there, looking from the top down, that's a right angle. And that's what you want in order to feel the QVB force. So usually, theta is 90 degrees, and the force, the magnetic force that's felt on that charged particle is the full QVB. So what direction is the force felt? This is given by the Spider-Man rule. And I'm actually going to write that up here because that would be a better idea. Your thumb, I'm not going to draw a hand this time because I suck at that, but your thumb is in the direction of the velocity of the charge, your index is in the direction of the B field, and then your middle finger, or the rest of your fingers as the case may be, extend in the direction of the force felt. So, in this particular case here, if I have a charge that's moving in this direction and a magnetic field is pointed outwards, I'm going to take my Spider-Man hand configuration and point my thumb in the direction of the of the velocity, point my finger in the direction of the magnetic field, and you can see my fingers naturally extend downwards, and that happens to be the direction of the force. So here we go. Okay, so you'll remember that if a charged particle enters a magnetic field sort of perpendicular to it, and it's a uniform magnetic field, then what's going to happen is that that charged particle is going to execute circular motion. And so I'm just going to cover some of the basics of that, the circular motion in a magnetic field. And it's not too bad. So QVB then is the force, the centripetal force, which means you can set that equal to mv squared over r, because that particle is executing now circular motion. There's a v on both sides, so we can simplify that a little bit, and we have sort of a master equation now that relates the amount of charge, the strength of the magnetic field, the mass, and the velocity of that particle to the radius of orbit. So we have this little relationship here. Sometimes a problem will ask for things in terms of period or frequency, and so there are times where you have to combine this with those facts, I suppose. So what I boxed just barely is, in fact, the kind of master equations for those types of scenarios. If I tell you that a charged particle is executing circular motion inside of a 3 Tesla field or whatever, tell me what the frequency is. It's possible to kind of mish and mash and combine these formulas in such a way that we can figure it out. So, okay, all right, but I'm not going to belabor that too much for reasons that'll probably be clear after you take the final. Okay, so wires also feel a force, right? And this is the LIB force that we joked about, LIB. And again, there is this extra phantom term that you've rarely seen me use, but again, it is important. So if theta is 0 degrees, that is, if the current is parallel to the B field, then no force is felt. And the way that works out mathematically is that the sine of theta, of course, goes to 0, because theta is 0 degrees. Usually we assume that they are perpendicular. So again, this is kind of the same thing we wrote above, but usually sine theta is equal to 1 because I is set up to be perpendicular to B. And so kind of just be aware of that. So just to run a quick example here, we have a wire, it's carrying 2 amps of current. I'm going to immerse it in a magnetic field that in this case is disappearing into the board. So here's my magnetic field here. And we're going to say that this is a 3 Tesla field, and this length here of the wire that's immersed in the field is 4 meters. And the question is what is the force? And I assume they're saying both the magnitude and the direction. So the magnitude's easy enough to get. FB is equal to LIB, the length of the wire, 4 meters, times the amount of current, 2 amps, times the strength of the magnetic field, that's 24 newtons. Bam! We've got the strength of the field there, or strength of the force felt. So what direction is it felt? Once again, we're going to use Spider-Man rule. So we have the wire pointed in this direction, the current's pointed in this direction. So I'm going to use my Spider-Man rule, extend my thumb in the direction of that current. My index finger needs to point in the direction of the magnetic field, which is into the board. So I'm going to whip that around. It looks like that. And you can see the rest of my fingers are pointed upwards, which happens to be the direction of the force. And so that's what we say. So it's FB is directed upwards. And then we're done with the problem. So that's it as far as magnetic fields go. We're not going to cover magnetic induction on the test, and that's not because I'm feeling especially lazy, although I might be doing that too. It's just I forgot to put it on the final, and so it's not going to be tested. But I do expect you to understand these principles here. That wires generate magnetic fields, and that moving charges also respond to those magnetic fields as well. So anyway, that's it, okay? Talk to you in a little bit. Bye.